Okay, so for those of you that tried to install SDPV, I'm sorry to put you through that. I hope some of you succeeded. I know some people succeeded, but I know others had trouble. So for those that did install it, you can follow along with what I'm doing. Go to this URL. And download the folder that's there, and that will have all the files in it that we'll be playing with all ready for you. Okay, so what's the summary so far? So we considered a 4-point function. And in the special case of identical scalars, it has the following form. And this function here has a conformal block expansion. It's a sum over operators O appearing in the phi OPE, squared OPE coefficients, one coefficient coming from each OPE that we had to do to evaluate the 4-point function, a conformal block, which depends on the dimension and spin of O, and we also had that this function has to be invariant under permutations of the points. And in particular, this gave us a constraint that g of u and v is equal to u over v to the delta phi times g of v comma u. Let's see. We also had that only even L's appear, and the dimensions satisfy unitarity bounds. So d minus 2 over 2 for L equals 0, and L plus d minus 2 for L greater than 0. Okay, so these are all the consequences of symmetry, conformal symmetry, and unitarity. And you can see that they take you pretty far. But not all is clear. This conformal block expansion picks out a particular channel, so it appears to break the permutation symmetry between these points. And so the consistency of this expansion with this equation is unclear. And just to give you a sense of the kinds of things that you need in order to satisfy this equation, let's look at a limit of the equation. So let's look at the small u limit. And you remember this u is x12 squared, x34 squared, over x13 squared, x24 squared. So this is the OPE limit where 1 and 2 are approaching each other. In this limit, the conformal blocks G delta L, thank you so much, of u comma v, we derived goes like u to the delta over 2 plus higher order in u. And there's some function of v that can also appear that that will not be so important, but you can imagine that it's there. It turns out that g delta L of v comma u goes like log u in the small u limit. Okay, so this is the conformal block in the usual channel, and this is the conformal block in the cross channel. And you can verify this. You remember we wrote down these expressions for the blocks in terms of hypergeometric functions. And this just comes at looking at a 2f1 in an expansion. So we had something like this, where beta were various numbers. The log comes from looking at this 2f1 in an expansion around x equals 1, as opposed to around x equals 0. OK, so let's look at the behavior of the two sides of this equation in this limit. So on the left-hand side, in the small u limit, the lowest dimension operator contributes. And which is that? Someone said it, I think. Yes, the identity operator. OK, so this is sum over all the operators, but the identity appears. And in particular, we should normalize phi so that the OP coefficient of the identity is 1. That's equivalent to normalizing its two-point function to be 1. OK, so this thing looks like 1 plus dot, dot, dot. On this side, what do we have? We have a sum over blocks. And each block looks like u to the delta phi from this prefactor here times log u plus dot, dot, dot. OK, so each individual block goes to 0 in the u goes to 0 limit, which means that there's no way a finite number of blocks can reproduce this one. You need an infinite number of blocks. And basically what happens is that the convergence of the conformal block expansion, basically as u gets smaller, the blocks that reproduce the 1 come from higher and higher dimension operators on this side. OK, so we need an infinite number of operators to solve this equation. So we have an infinite number of products of hypergeometric functions with some coefficients and some dimensions that we don't know. It's a very complicated system. And people stared at these equations for decades without making any progress, in higher dimensions at least, towards solving the equations. In 2D, of course, you can make lots of progress, but that's because of the additional symmetries that are present. And what was thought was just that, well, there's not enough symmetry in higher dimensions. Conformal symmetry gets you only so far, but now you're stuck. But there was a new idea. So this idea is due to Rotazzi, Richkoff, Tani, and Vicky in 2008. And their idea was, well, maybe we can't just solve this equation exactly. But perhaps we can extract useful information out of it nonetheless. And in particular, they thought, well, let's look at this equation geometrically and see what that implies. So OK, so let's write it in the following way. We have a sum over operators O, f phi phi O squared. And I'll just take everything and put it all on one side of the equation. So, and I'll multiply through by v to the delta phi. So on this side, so this is coming from the left-hand side of the crossing equation, multiplied by v to the delta phi. And then we subtract the right-hand side, which looks like this. And let's call this quantity f delta phi delta L of u and v. So the key observation here is that, okay, these special functions are known. And these coefficients, well, we don't know what they are, but we can say that they're positive, which is a consequence of unitarity. So in particular, the OP coefficients of real operators are real. You could think of this as just, well, these OP coefficients are 3-point function coefficients. And reflection positivity implies that 3-point function coefficients of real operators have to be real. Yes? So the easiest way to do it is to just put the 3 points on a line and consider reflections in this direction. So the products of distances between the points will not change, and those are just positive real numbers. So you get that the coefficient is a positive real number. Okay, good. So this is not just any system of equations. It has positive coefficients. So we can think of these functions here as vectors. In the vector space of functions of u and v. And then what we have here is we have a bunch of vectors, f delta 1, L1, f delta 2, L2, and so on. And we're asking, is it possible for these vectors to sum to 0? Oh, I forgot the equation. Is this a 0? Is it possible for these vectors to sum to 0 with positive coefficients? And the answer is, well, it depends on the vectors. So in this case, it's not possible. If, let's say, these are all the vectors that we have. But in something like that, then it is maybe possible. So here the positive cone spanned by these vectors contains the origin, and here it doesn't. And the way to distinguish between these two cases is, well, in the first case we can find a plane through the origin. Okay, so the plane goes through the origin, and all the vectors lie on one side of the plane. Okay, so I'll call this plane alpha, and I'll call it a separating plane. Okay, so the idea is you plot all the vectors that can appear, and then you ask, can I find a separating plane or not? And it's not actually obvious that you should be able to get anything out of this, but let's do an example, and we'll see that it's actually quite powerful. So any questions? Yes? That's right. So there isn't really a nice. Yeah. So the reason is that there is a nice basis for conformal blocks. They satisfy a conformal Casimir equation. So they have nice properties. But as soon as you take a difference of cross blocks, you ruin all of that. This thing satisfies no nice differential equation that I know of, and there really isn't a nice structure that I know of on these functions.
And just to remind at this point, you have no idea what the f's are except that they're positive.
Well, okay. So we know we don't know what the deltas are. Oh, sorry. Yes, exactly. We don't have any idea what the little f's are, except we know their squares are positive, and we have no idea what the deltas are either. The only thing we know is the form of this special function. You could ask, like, why on earth would there be a situation where all the functions are pointing in one direction? Why aren't they all kind of random? One quick answer is that the conformal blocks themselves have some positivity built into them. And that comes from the fact that you can think of them as an overlap of states. So we have x1 and x2 on the cylinder, and x3 and x4 up here. And all we've done is inserted a projector O between them. And you can see that the projector O doesn't care about, if I do a reflection, the projector O doesn't affect anything. So you should still have reflection positivity for the blocks. In particular, if you pick the configurations of points so that they're symmetrically arranged around a flip in dilatation time, then the block must be positive. So the blocks have positivity built into them. So it makes sense that maybe they're always pointing in a particular direction. Other questions? Yes? So the blocks, you can use the recursion relation to compute the blocks and then just take the difference to get this difference. But yeah, you could probably also write down a recursion for the difference itself. Other questions? Okay. Good. So let's do an example. And I should say that this example is due to Pedro and Joao, Joao you'll meet next week. But it's a beautiful, very simple example where you can see everything. So let me define these new functions h of z and z bar to be just our f functions from before divided by the unit operator f. Okay, this is just the definition for convenience. And remember that u and v in terms of z and z bar look like this. And what we're going to do is we're going to plot vectors associated to these functions that are two-component vectors of the following form. So that's the first component. Second component is okay, so you can think of this thing. What this thing is doing is it's just, so this lives in an infinite dimensional space. And we're just projecting it onto a two-dimensional subspace. Everyone okay with that? Okay, good. So let's, and I should say that for this example, we're going to work in 2D. Where the blocks have the form that I wrote in terms of hypergeometric functions. So let's take a look. All right. So what I'm going to do is already in one of the files you downloaded. It's a 2D vectors example, but I'll just code it up from scratch so that people can follow along. So first, let's define the conformal blocks. So we had this function, which was a hypergeometric function. Yes, that's a great idea. That's probably not even enough. How's that? Great. Okay. So we had this hypergeometric function. Was z to the beta over 2, hypergeometric to f1 beta over 2, beta over 2, beta z. That was our SL2 block. And then the 2D conformal block was a function of delta and L, and z bar. And that was k of delta plus L z, k of delta minus L z bar, plus k of delta plus L z bar, k of delta minus L z. And then I have this function h that I've defined, which is a function of delta phi, delta and L, and z bar. Okay, so what is this? So first we need v to the delta phi times a conformal block, u to the delta phi times the cross-channel conformal block. And so swapping u and v, what does that do to z and z bar? Not quite. So yeah, if you look at this formula here, you see that swapping u and v just corresponds to swapping z with 1 minus z and z bar with 1 minus z bar. At least that suffices to swap u and v, and you can convince yourself that that actually is the right prescription. Okay, so that was our f function. And now let's divide by the f function for the unit operator. And the conformal block of the unit operator is just 1. So we just get these. Okay. And let's see. We also had a vector that we were making out of an h function, which was h of 1/2 3/5 minus h of 1/2 1/3. I don't have to be that precise about this. H of 1/2 3/5 minus h of 1/3 1/4. And for display purposes, so for figuring out whether these vectors can sum to 0 with positive coefficients, the normalization of the vectors doesn't matter very much. So I'm going to define a normalization that looks good in the display. Okay, so the vector we care about is this vector of h of delta phi, delta, and L. And we'll give it some arbitrary normalization, which will depend on the spin. And you'll see why I picked this in a moment. Okay, and so the normalized vector is just this scale factor times the vector over the norm of the vector. Okay, so any questions about the code so far? None? Okay, so good. So we just have these vectors defined, and now let's plot them. So let's take the specific case of delta phi is 1/8. That I happen to know is the dimension of the spin field in the 2D Ising model. Okay, so that's why it's interesting. And we have to plot these vectors as a function of delta. And to solve this crossing equation, in principle, we can have any delta obeying the unitarity bound. So what I'll do is I'll write delta is L plus tau, where tau is bigger than or equal to 0. So that's the unitarity bound in 2 dimensions. Tau is sometimes called the twist. Okay, and because we're on a computer, we can't. I'm going to plot it for just a finite range of tau from 0.1 to 4. That will be enough to see what's going on. I'll plot vectors up to spin 14. And I'll explain what delta scalar min is supposed to do in a moment. And there will be a couple objects that will be important for us. One of them is the stress tensor vector, and another is the table of all the block vectors. Okay, so the stress tensor vector is a normalized vector of delta phi, and the stress tensor has spin 2 and dimension 2. For the block vectors, we'll have a table of normalized vectors, delta phi, tau, L. From L goes to 0 to L max. What should the step be in L? 2. Why 2? Right, no odd spin operators. Good. Okay, so that step is 2. And then we'll scan over tau. We'll go from, so let's see. I think I may have made a mistake in my previous version of the notebook, but that's okay. Oh, yeah, I know what the problem is. So the dimension is tau plus L. From tau min to tau max. And we'll give it a different step for the scalars, because we'll need to see the scalars in higher resolution than everything else. Okay, so those are our block vectors. And now let's plot them. So list plot block vectors. And we'll make this look nice. Okay. So here we go. All right, so that's pretty crazy looking. What are all of these things? This is the scalar vector, as you dial delta. So that's delta equals 0, and then we dial it up. It does this. It goes around and comes back. And that's delta equals 4, and it just converges as delta goes to infinity. This one is spin 2, the stress tensor. And the stress tensor lives here at this end, and then those are the high dimension spin 2 operators. This is spin 4, spin 6, spin 8, and so on. And let me show the stress tensor vector. just to give a point of reference. And I'll draw a line between the stress tensor vector and minus the stress tensor vector. Oh, I made a mistake. Let's see. I just went from 0.1. Let's go from 0.01 for tau min. Okay, good. So now you can see that this is the stress tensor, and this is minus the stress tensor. All right, so if we have all these operators present in the theory, then just based on this plot, is it possible to solve crossing symmetry? Let's get an opinion from everyone. Yeah. Well, who says it's possible to solve crossing symmetry? Okay, and who says it's not? Okay, good. Right. It's possible. So one trivial solution is only the stress tensor, no higher spin operators, and then a scalar up here. Okay. So that obviously doesn't solve the full crossing equation, but it does solve the crossing equation in this subspace. In the space of functions of two variables that we've taken. Okay, so we're plotting a particular subspace, and there it looks like we can perfectly well just have the stress tensor and a scalar, and we're totally fine. Okay, so now, well, okay, what if we? So here we're allowing all operators consistent with the unitarity bound. What if we start making some assumptions about the theory? So let's assume that all the scalars appearing have dimension larger than some value. Okay, so let's say larger than 0.1. And so that means that for the scalars, I should go from delta scalar min, and otherwise I should start from tau min. Thank you. Good. Okay. So I'm going to, you know what the code looks like, so I'm going to zoom out to make it so that I can manipulate things and replot them. Okay. So, good. So delta scalar min is 0.1. And you remember this was a scalar with dimension 0. So what we'll do is we'll shave away a little bit of this curve down here. Okay, and indeed we just shaved a little bit away. It's moved over slightly. Okay, so that's not a very strong assumption about our theory. Let's assume that all scalars have dimension bigger than 0.3. Wow. Okay, so we just lost a huge amount of the curve. Let me do that less quickly. So 0.2, I'm going to zoom out so that the screen stops moving. Okay, scalars with dimension bigger than 0.2. Okay, 1, 5. Good. Okay, so you can see that somewhere between 0.1 and 0.2, this curve starts to disappear rapidly. And the reason for the bumpiness is because we're interpolating. So there are just a few points that are being plotted here, and it's interpolating. Okay, good. So what if I set delta scalar min equal to 2? All right, so now almost the whole curve has disappeared, and these are the scalars. So now let's ask, is it possible to solve crossing symmetry in this case? No, it's not. All the vectors lie on one side of a separating plane. I could take the plane to be this or whatever. They're all on one side. And even though we're just plotting things in 2 dimensions, we can conclude rigorously from this plot that it's not possible to solve the whole crossing equation because this plot gives a proof by contradiction that the entire crossing equation can't be solved in this case. Okay? So the conclusion is that there do not exist 2D unitary CFTs with a dimension 1/8 scalar operator such that all the scalars in the OPE of that operator with itself have dimension larger than 2. Yes? Right. Oh, good question. So the spins, you can already see sort of what's happening. They just converge in a very simple way. So in particular, this separating plane here, you can prove analytically, if you like, that the large spin blocks lie on one side of this separating plane. So yeah, so I picked some arbitrary L max and delta max, and the reason is because things are just converging at large spin and large delta. Yeah, I mean, you know all these functions. They're hypergeometric functions. So you can just compute their asymptotic behavior. Good question. Okay, so this is the core logic in this technique. So please ask questions. Yes? So how do you get started with these techniques?
Yes. Because here you started off by saying that
Oh, you're saying you're an experimentalist, and you.
there are no CFTs that behave for a set of properties, but whether
Good. So you'll have to wait a few minutes. Other questions? Good. So let's suppose that crossing held that equation. Let's suppose that it holds. Now let's evaluate that equation at these points. Okay. Now I claim, if we look at the second component, if we look at minus this, then it's positive block by block. But that means it's not possible to solve that equation with positive coefficients. So what you do, so this is our separating plane in this case, alpha of h. So we have our equation that says that sum over O of f phi O squared h delta L is 0. And we want to know if this is possible. So let's assume it is. Now apply alpha. We get sum over O f phi O squared alpha of h delta L equals 0. But this is greater than 0, and this is greater than 0. So you're screwed. Okay, so all we need is one functional. It's an infinite dimensional space, but by looking at the dual space, we can prove things about it without an infinite amount of work. If you want to interpret it as an inner product, I mean, I would say it's more the expectation value of those three operators in the vacuum state. It just has to be real. It doesn't have to be positive. So when you take this correlator and you take its Hermitian conjugate, then so the real thing to do is to just take. Here, probably shouldn't have said anything about reflection positivity. Let's just take this 3-point function, 5 phi of x, phi of y, O of z. And let's think in Minkowski signature. So these are now Minkowski points. So then the operators they're not reflection Hermitian, they're just Hermitian. Okay? And so now take star of this is time ordered. This had better just be equal to itself. Because all the operators are Hermitian.
So is unitarity coming about?
This is unitarity. I mean, the fact that you have Hermitian conjugation, and it's consistent with the taking expectation values and inner products is also consequence of unitarity. Yes. How hard is it to pick those numbers? Pedro, how hard is it to pick these numbers?
I mean, any numbers more or less work. What did you pick 0 and 1? It's good to pick on close to 1/2. Because 1/2 is 1/2 is a point where the point if 1/2 1/2, you can think of them as being in a square.
Yeah.
So you choose points relatively close to 1/2.
Okay. Good. So we disproved a statement about CFTs. We showed that there must exist a scalar operator with dimension less than 2. And we can do better. So what if we have delta scalar min is 1.5? Well, we still can't solve crossing. 1.2, still can't solve crossing. 1.1, still can't solve crossing. 1.01, okay, now we can. And the crossover point is about 1.036. So the conclusion is that there exists a scalar with dimension delta less than 1.036. So this is in a 2D CFT with a scalar operator with dimension 1/8. So does anybody know what the dimension of the lowest dimension scalar appearing in the sigma sigma OPE is in the 2D Ising model? Yes. Speak up. 1. Okay. So actual answer. One. Okay. So this bound, it looked like we were just doing kind of crazy ad hoc things, but the bound is actually nearly saturated at the 4% level, just by this simple exercise.
Move around as you change these numbers that Pedro said don't matter much.
Yeah, that's right. So the bound that you can get depends on which functional you choose.
You can do some variational method thing to try a bunch of different ones and try to get that further down.
Exactly, and that's what we're going to do next. So the idea is you get different bounds depending on different functionals. So we should pick the functional that gives the best possible bound. Different points.
The different plugins in Conformal.
these. Yeah, sorry. That's what I meant by functional. I guess I was jumping ahead a little bit. But yeah, I mean, if you plot different points, then you get different bounds. Like the picture will just look different, and this exercise that we do will give a different answer. So you need to pick the points that give the best possible bound. Yes?
It seems pretty, it's important that you get to say that you can have like an exact example or being put out at the same time. Or bigger subspaces, higher dimensions, etc. Is it just the numeric?
So I think I have time. So next, what I'm going to do is show you how these computations are actually done, how to get the really very best bounds, and you'll see that the asymptotics are under good control with these techniques. Okay. But this is just to give you a flavor of why the bounds exist. So let's generalize what we did. We start by making an assumption about the spectrum. And as an example, we said that all scalars have dimension bigger than some delta min. So that's what we were doing there. And so now we try to find a separating plane. So a separating plane is a functional that takes a function of two variables to the real numbers, such that this functional is positive for all delta and L in the spectrum. So what that means in our example is that we have to demand positivity for delta bigger than L plus d minus 2 when L is bigger than 0, and delta bigger than delta min for L equals 0. Okay, so this is where our assumption enters. Our assumption about the spectrum enters in the delta and L for which we demand positivity. So if we succeed in finding such an alpha, then the spectrum that we hypothesized is ruled out. And the logic for that is exactly this here. We assume there's a solution to crossing, then we apply alpha to it, and we get a contradiction. Okay, so now I'm going to talk about the numerical techniques the most modern numerical techniques that one can use to try to solve these kinds of problems. And I should say the most difficult step here is in finding some functional. Okay, this functional has to satisfy all these inequalities, and it's actually an infinite number of inequalities. So you have all these constraints, and you have to solve them. So this is an optimization problem, basically. It's an example of basically an infinite dimensional, infinite number of constraints linear programming problem. A lot of the work that's been happening since this paper has involved coming up with efficient techniques for solving these kinds of infinite problems, infinite optimization problems. The types of things that people have done to deal with this infinity. So we have infinite inequalities in infinite dimensions. So the first thing, the solution to the problem of infinite dimensions, we've already seen. You just look in a finite dimensional space of functionals. So if you look in a small dimensional space, you'll get some bounds. They may not be the best bounds. If you look in a larger dimensional space, you could get better bounds. And eventually, you want to take the dimension of the space you look in as big as possible, and then you'll get the best possible bounds. Okay, so as an example, for what comes next, we're going to look at a particular subspace of functionals, which are a sum of derivatives. A sum over derivatives m and n with respect to z and z bar of f around the crossing symmetric point, z equals z bar equals 1/2. Okay, and our finite dimensional space will just be, we'll look at up to a finite number of derivatives, lambda. So that solves that infinity. We've had to compromise in that we may not get all the information possible, but at least we'll still get true rigorous information in the same sense that this was rigorous and true, even though we only worked in 2 dimensions. Okay, so this other one is trickier. People have done a few different things. One is to discretize the deltas. So you take your continuously infinite number of constraints, you just chop up the deltas into very fine steps, and you turn it into a very large finite number of constraints. Once you have a finite number of constraints of linear inequalities in a finite dimensional space, that's called a linear programming problem, and this is something you can solve on a computer. And this is what was originally done in the paper by Ratazzi, Rychkov, Tani, and Vicky. Another thing that people have done is write a custom LP solver that can deal with this infinite number of constraints. And the technique that I'll talk about today is something called semi-definite programming. This has the advantage of being pretty fast, dealing nicely with the asymptotics, and not requiring any sort of discretization in the dimensions. Okay, so what is semi-definite programming? So with semi-definite programming, we can solve problems of the following form. Find a vector A such that A dot a vector of polynomials is greater than 0 for all x bigger than or equal to 0. So we have constraints that look like this. We have alpha of f delta L delta phi. This is a sum over derivatives a mn dm dn with respect to z and z bar of f delta phi delta L z z bar at the crossing symmetric point. And this has to be bigger than or equal to 0. So we can use semi-definite programming if we can write this thing, or approximate this thing, as a sum of AMN times polynomials in delta times some positive function of delta. Okay, so in particular, the way we would use it is we would write delta is delta min depending on L plus x. So delta min L would be either the unitarity bound for large L, for L greater than 0, or this delta min that we pick for the scalars. And now, well, if we have a positive function of delta, then it doesn't matter in this inequality. And so now we have an inequality of the form sum over mn of amn times polynomials in x is bigger than or equal to 0 for all x bigger than or equal to 0. No. 1x. Good. Okay. So yeah, actually, thank you. So you can have more than one of these constraints. Okay. So each constraint is a univariate constraint. So we would have here J corresponds to L. So maybe I should just write it as L. Okay, so there's a single variable polynomial for each L. This is a times, not an x. Okay, so I'm yes. This here. Okay, so so I claim that if we can take this junk and write it as a sum of polynomials in delta times a positive function of delta, then we can apply semi-definite programming. So this is a sum over amn, the coefficients in our functional alpha, times polynomials of delta. And this is some positive function of delta. Okay? This is, I'll rewrite it. So the way we apply semi-definite programming is we write delta is equal to delta min of L plus x, where x is bigger than or equal to 0. Yes? Yes, the positive function can depend on L. Let me give it a name. Yes.
How did you define this alpha? Oh, how did you write down the value?
So alpha is defined here.
Yeah. How do you get it from the conformal transformation?
So this is an arbitrary choice. I'm choosing to look at functionals of this form. So over there, I chose to look at functionals of the form h at one point minus h at another point. But in general, all I'm doing is applying a linear functional to h. So you can evaluate it at different points. You can take sums of values at different points. You can take sums of derivatives at different points. Whatever you like. Good. So z equals z bar equals a half is the crossing symmetric point. It's the point at which both channels for the conformal block expansion converge equally well. And so basically what we're doing is we're sitting on that point, and then we're just probing a neighborhood at that point. It's not obvious that this is the best thing to do. And actually, it's sort of a historical accident that people looked at functionals of this form. But it does turn out to be important for semi-definite programming to use these kinds of functionals. So I should say it's worth exploring other kinds of functionals. That's something that really hasn't been done enough. And there's an infinite dimensional space, so there's lots of room to play around. And we don't know what the optimal functionals look like. Good. So on a computer, yes, semi-definite programming needs a finite number of L's. So L from 0 up to L max. And here is one case where you have to be careful about asymptotics. Here you really need to truncate the number of spins. And so you need to make sure that the answers you get don't change when you change L max. The infinity that this, the asymptotic thing that this does deal with is this approximation turns out to be asymptotically good at large delta. So the large delta behavior is totally under control. The large L behavior is something you have to worry about. The blocks always converge at sufficiently large L. It's just a question of how large you need to take it. Yes? So I haven't proved this yet. So if we can find an approximation like this, then we can apply semi-definite programming. The reason I wrote a wavy equals is because this will not literally be true. There do not exist polynomials such that this is true. On the other hand, there exists a family of polynomials that arbitrarily well approximate the blocks in this way. These are polynomials. So the P and MNs are polynomials, and the Chi's are not necessarily polynomials. Yeah, I mean, Chi's times polynomials. Yeah, I mean, they will correctly reproduce the asymptotics. That is an excellent question. Let me show you an example of coming up with this approximation, and that will be made clear. Okay, so I just said if we can find such a thing, then we can apply semi-definite programming. This is historically what we started with. We just said, oh, well, there's this great technique, semi-definite programming. Can we possibly apply it? And it turns out that you can, and it's actually it follows from the conformal algebra that there exist exponentially good approximations to derivatives of the blocks in terms of polynomials. And I won't show you why that is in complete generality here, but I'll just demonstrate an example. which are SL2 blocks, which were just these hypergeometric functions. So the SL2 blocks, we had this function k beta of z. There's a hypergeometric transformation that lets you write this in terms of a different variable, which I'll define in a moment. Okay, and here rho is z over 1 plus square root of 1 minus z squared. So rho turns out to be the right variable to think about conformal blocks in. And I won't explain that here, but it's in the lecture notes that are on the wiki. So you can have a look at that, and it'll explain the rho variable. Okay, so good. So this is this k beta of z. This was the holomorphic part of the 2D conformal block. And so this thing has, oh, and I should say that rho of z equals 1/2 is about 0.17. So it's 3 minus 2 root 2. So if we do a power series in rho, we get a pretty rapidly convergent expansion. And it looks like this. Okay, so now I can answer your question. The blocks do indeed have poles in delta. So remember here, beta in the 2D blocks was delta plus L and delta minus L. So there are indeed poles at negative integer values of beta. But the poles will always occur at values of delta that violate the unitarity bound. The reason is because the unitarity bound comes from demanding that all descendants have positive norm. And the poles are coming from dividing by norms of descendants. So the poles are guaranteed to be positive in a unitary theory. So there are poles in delta, but they're in a region where you don't care. So the idea to get a polynomial approximation is to truncate this at some large order. And then you get that this is equal to rho to the beta over 2 over a product of poles up to your truncation order, beta plus k, times some polynomial in beta and rho. So when you take derivatives, at 1/2, what do the derivatives do? Well, they can act on this and adjust the coefficients of this, and you can also bring down powers of beta from this thing. But you just get that this is equal to the crossing symmetric value of rho, which I'll call rho star. So this is just rho star to the beta over 2 minus product of poles over product of poles times some polynomial in beta. So the validity of this approximation is controlled by how many terms you keep in this sum. Each term is suppressed by 0.17 to the 2k, so 0.0 something to the 2k. So it converges extremely rapidly. And the other property is that each term is bounded as delta goes to infinity, or beta goes to infinity. So you can see you have equal powers of beta on the top and the bottom. So the convergence, as you take more and more terms, is actually uniform for all beta. So it's a very, very well-behaved approximation. So by using this approximation, along with the formula for the 2D conformal blocks, you can verify that there is a formula of the form we wanted here. Basically, this positive function is a product of the positive functions out front for each, for the holomorphic block and the anti-holomorphic block. So that rho star to the beta over 2 over a product of betas, you just get 2 copies of that. That's the positive function, and then the polynomials are the products of the polynomial from the anti-holomorphic part and the holomorphic part. So this looks like it's very special to 2D, but also 4D, they also depend on these functions, so you can do the same thing in 4D. And it turns out that actually this structure is very general and holds in any number of dimensions. That's a consequence of the conformal algebra, and I can maybe tell you about that offline. Questions?
Relies on the fact that we know the form of the form.
Uh-huh.
But
Right. So the question is, we don't have, in odd dimensions, we don't have expressions for the conformal blocks in terms of elementary functions, like we do in even dimensions. So how do you do this? And the answer is that you need a way to compute these approximations for the blocks to arbitrarily good approximation. For that, there are a number of techniques. One of them is you can just solve the conformal Casimir equation order by order in rho. And that just gives you the answer. Yes. Yes. Yeah, that's actually a consequence of conformal invariant of the conformal algebra. The poles are at negative integer values of delta, sometimes negative half integers. There are experts on this fact in the audience, so I can introduce you to them. Yeah. Good. Other questions? Yes. Nope. The same tricks work for every conformal block. Non-identical operator dimensions, operators with spin, superconformal blocks with spin, whatever you want. It's Virasoro blocks, super Virasoro blocks, W algebra blocks, all your blocks. It works for all the blocks, and it's a consequence of the conformal algebra. Okay, so Tom's disappointed. I haven't. So does that mean I get to keep going?
Bullets don't stop you people, but you have a free hour this afternoon, I guess. I'm not in charge.
So the question is, yeah, should I keep going now or?
But it must have a one-line answer. I want to know what the
Yeah, but I don't want to give away the punchline. So should I continue now or should I continue later? It's hard for me to predict. Try. Okay.
We're supposed to have a half-hour break, and then there's 2 more talks.
Okay. How about 20 minutes? Is that okay? I could do it later. Okay. Yep, I've summarized everything. Yeah. Okay. Okay.